In astrodynamics or celestial mechanics, an elliptic orbit is a Kepler orbit with the eccentricity less than 1. This includes the special case of a circular orbit, with eccentricity equal to 0. In a stricter sense, it is a Kepler orbit with the eccentricity greater than 0 and less than 1. In a wider sense, it is a Kepler orbit with negative energy. This includes the radial elliptic orbit, with eccentricity equal to 1. In a gravitational two-body problem with negative energy, both bodies follow similar elliptic orbits with the same orbital period around their common barycenter. Also, the relative position of one body with respect to the other follows an elliptic orbit. Examples of elliptic orbits include Hohmann transfer orbit, Molniya orbit and Tundran orbit. Velocity. Under standard assumptions, the orbital speed of a body traveling along an elliptic orbit can be computed from the Vis-Viva equation as where is the standard gravitational parameter, is the distance between the orbiting bodies, is the length of the semi-major axis. The velocity equation for a hyperbolic trajectory has either plus, or it is the same, with the convention that in that case A is negative. Orbital period. Under standard assumptions, the orbital period of a body traveling along an elliptic orbit can be computed as where is the standard gravitational parameter, is the length of the semi-major axis. Conclusions. The orbital period is equal to that for a circular orbit with the orbital radius equal to the semi-major axis. For a given semi-major axis, the orbital period does not depend on the eccentricity. Energy. Under standard assumptions, specific orbital energy of elliptic orbit is negative, and the orbital energy conservation equation for this orbit can take the form where is the orbital speed of the orbiting body, is the distance of the orbiting body from the central body, is the length of the semi-major axis, is the standard gravitational parameter. Conclusions. For a given semi-major axis, the specific orbital energy is independent of the eccentricity. Using the virial theorem, we find the time average of the specific potential energy is equal to -2 I micron, the time average of ρ1 is or1. The time average of the specific kinetic energy is equal to I micron. Flight path angle. The flight path angle is the angle between the orbiting body's velocity vector and the local horizontal. Under standard assumptions, the flight path angle satisfies the equation where is the specific relative angular momentum of the orbit, is the orbital speed of the orbiting body, is the radial distance of the orbiting body from the central body, is the flight path angle. Equation of motion, see orbit equation. Orbital parameters. The state of an orbiting body at any given time is defined by the orbiting body's position and velocity with respect to the central body, which can be represented by the three-dimensional Cartesian coordinates and the similar Cartesian components of the orbiting body's velocity. This set of 6 variables, together with time, are called the orbital state vectors. Given the masses of the two bodies, they determine the full orbit. The two most general cases with these 6 degrees of freedom are the elliptic and the hyperbolic orbit. Special cases with fewer degrees of freedom are the circular and parabolic orbit. Because at least 6 variables are absolutely required to completely represent an elliptic orbit with this set of parameters, then 6 variables are required to represent an orbit with any set of parameters. Another set of 6 parameters that are commonly used are the orbital elements. Solar system. In the solar system, planets, asteroids, most comets and some pieces of space debris have approximately elliptical orbits around the Sun. Strictly speaking, both bodies revolve around the same focus of the ellipse, the one closer to the more massive body, but when one body is significantly more massive, such as the Sun in relation to the Earth, the focus may be contained within a larger massing body, and thus the smaller is said to revolve around it. The following chart of the perihelion and aphelion of the planets, dwarf planets and Halley's Comet demonstrates the variation of the eccentricity of their elliptical orbits. For similar distances from the Sun, wider bars denote greater eccentricity. Note the almost zero eccentricity of Earth and Venus compared to the enormous eccentricity of Halley's Comet and Eris. Radial elliptic trajectory. A radial trajectory can be a double-line segment, which is a degenerate ellipse with semi-minor axis equals 0 and eccentricity equals 1. Although the eccentricity is 1, This is not a parabolic orbit. Most properties and formulas of elliptic orbits apply. However, the orbit cannot be closed. It is an open orbit corresponding to the part of the degenerate ellipse from the moment the bodies touch each other and move away from each other until they touch each other again. In the case of point masses, one full orbit is possible, starting and ending with a singularity. The velocities at the start and end are infinite in opposite directions and the potential energy is equal to -infinity. The radial elliptic trajectory is the solution of a two-body problem with at some instant zero speed, as in the case of dropping an object. See also free-fall inverse square law gravitational field. History. The Babylonians were the first to realize that the Sun's motion along the ecliptic was not uniform, though they were unaware of why this was. It is today known that this is due to the Earth moving in an elliptic orbit around the Sun, with the Earth moving faster when it is nearer to the Sun at perihelion and moving slower when it is farther away at aphelion. In the 17th century, Johannes Kepler discovered that the orbits along which the planets travel around the Sun are ellipses with the Sun at one focus, and described this in his first law of planetary motion. Later, Isaac Newton explained this as a corollary of his law of universal gravitation. See also, characteristic energy, ellipse, list of orbits, orbital eccentricity, orbital equation, parabolic trajectory. References. Further reading, Euro unregistered trademark Eliseo, The First Order Orbital Equation. American Journal of Physics 75, 352 Euro 355. Bibcode, 2007 MJPH 75 352 DDoI, 10.1119/1.24322126. Euro unregistered trademark Eliseo, Mironov, Sergei 5. The Gravitational Ellipse. Journal of Mathematical Physics 50, 022901 Euro 022901. AR-ZIV, 0802.2435. Bibcode, 2009 JMP, 582901 MDOI, 10.1063/1.3078419. Curtis, Howard. Orbital Mechanics for Engineering Students. Butterworth Heinemann. ISBN 978-0123747785. External links, JavaPlot animating the orbit of a satellite in an elliptic Kepler orbit around the Earth with any value for semi-major axis and eccentricity. Apogee, Perigee lunar photographic comparison, aphelion, perihelion solar photographic comparison, http://www.caster2car02 or beatsindex.html